Okay, I'm making a video to help go over the lab for anybody who was absent the day we did the lab or the day that we went over the lab. So for this lab, the title of the experiment is going to be finding the empirical formula of an ionic compound. Okay. You need to put your name, the period, the date. Don't worry about partners. Don't worry about the experiment number. All right, for the problem in this experiment was to determine the molar ratio of magnesium and oxygen in an ionic compound. Okay. The hypothesis. Well, what we did was we burned a piece of magnesium metal. The magnesium metal looks like this. It's just a regular piece of magnesium metal. When we burned this, it reacted with oxygen in the air and it formed a product that looked like ash. The ash would be like something that you got from like a fire or something. Here's some example. So looks like ash. All right, that ash, that product was the magnesium oxide. Well, the question was, do you think that this magnesium, the mass of the magnesium, initially, so if I put this on a balance and I got the mass, do you think that the mass is going to increase, decrease, or stay the same after you burn it? Well, let's just say, I think the mass of magnesium, Mg, capital Mg, will decrease after burning. Maybe, who knows? That's my hypothesis. And now I'm going to say because the fire will consume the metal. That's my reasoning. I don't know, but I'm just hypothesizing. All right, my objective is to compare the theoretical formula of magnesium oxide, the compound that we're going to form, to the experimental formula. Which will be found by combining magnesium and oxygen. Okay? So the objective is to compare the theoretical formula of magnesium oxide to the experimental formula, and the experimental formula will be found by combining magnesium and oxygen. So the way that I'm going to combine magnesium and oxygen is by taking the piece of magnesium metal and putting it inside of a crucible, like that. Then I'm going to have a ring stand. I don't have the ring stand right now, but if I did, I would put the crucible over the Bunsen burner, not like that. This is just because I don't have a ring stand. The ring stand would hold it up at a certain height, but I don't have it. And what happened is that the Bunsen burner, the flame would heat the bottom of the crucible, and then the magnesium would react. Well, if there's heat, that magnesium will react with the oxygen in the air and form a product called magnesium oxide. So, the variables in this experiment is the amount of magnesium, because let's say that I put in this little teeny tiny strip of magnesium. It's going to take a lot less time to heat up or burn this teeny tiny strip than it would if I put in maybe like a chunk of magnesium the size of this, right? Let's say if I tried to react a chunk of magnesium like that, it would take a lot more time than a chunk of magnesium like this. So the amount of magnesium is definitely a variable to consider. The next thing is the time allowed to heat. So the time allowed to heat is another variable. If I allow this magnesium to heat for 10 minutes, the reaction might come to completion. But let's say I only allowed it to react for 5 minutes. Do you think that that reaction is going to complete? Probably not. So the time allowed to heat is another variable to consider. And the last thing is the amount of product that I produce. So amount of product produced. So depending on how much magnesium and depending on how much time I allow that magnesium to burn, I'm going to produce a specific amount of product. It's going to depend, again, on the amount I start off with and how much time I allow that to react. Hopefully, I give it enough time to completely react so I can produce the maximum amount of product. But if I didn't give it enough time, I'm going to have less product than I actually could. If I gave more magnesium, I'm going to form more product. If I had less magnesium, I'm going to have less product. So these are the 3 variables. For safety, Bunsen burners. So Bunsen burners must never be left alone when lit. Okay, so when we're working with Bunsen burners, this little piece of equipment, if this guy is on, if he has fire, we always have to have an eye on it. Can't leave it alone. All right, coming down here. Down here, this is the data that you should have gotten. So in the lab, you would have gotten the mass of an empty crucible. I'm going to give you some numbers. So let's say right now I go and I get the mass of this crucible. I put it on a balance, I put it on a scale, and I got the mass. Let's say that that mass was 16.74 grams. Okay? Then I'm going to take the piece of magnesium metal and I'm going to put it inside the crucible and I'm going to get the mass again. Let's say that mass was 16.81 grams. All right, well now I need to find the mass of just the metal. Well, this is the mass of the empty crucible, and then this is the crucible plus the metal. If I want just the metal, all I have to do is take away the crucible. Whatever's left is the metal. So 16.81 minus 16.74. Let's see what I get. One minus 4, that's like 11 minus 4, which is what? Oh my God, 7? I can't even do math. Okay, 7. And then 7 minus 7 is 0, 0, 0. So 0.07. And that's the mass of the metal. So that little piece of metal right there, that would be the mass of that metal. All right, the next part says I'm going to heat it for 10 minutes and then I'm going to allow it to cool. It should look like a gray powder after. Again, it should kind of look something like that ash right there. All right, so if I did that, I would end up getting a number. I would put it, the ash, all of that, I'd put it on a scale and I'd get the mass. And I did that and I got 16.85 grams. Well, coming back to our hypothesis, do you guys remember we asked ourselves whether the mass was going to go up or down? Well, I said I thought the mass was going to decrease. But what really happened? The mass actually increased. See, here's the magnesium metal plus the crucible before heating, and here it is after heating. It actually increased by 0.04. So that 0.04, where did that come from? That was the mass of the oxygen that was added, right? So in this experiment, we had magnesium. It was a solid, and it reacted with oxygen in the air, which was a gas. When these two guys come together, we form a product called magnesium oxide. Notice, the final product is not just magnesium, it's now magnesium and oxygen. So this extra mass is the oxygen that was added to the magnesium. All right, and just for the sake of balancing, all right, we'll talk about that when we come back from break, don't worry. All right, coming down here to the calculations. Number 1, it says to find the moles of magnesium. Well, this is a conversion problem. It did give you a formula, but I'm not going to use that formula. Yes, if you take the mass and you divide it by the molar mass, you will get moles. But you guys should remember that we always do conversions. So in any conversion problem, the first step is to write down your given. My given is going to be the mass of the magnesium. Notice, the mass of the magnesium is 0.07 grams. So I'm going to write down here 0.07 grams, and that's of magnesium. Anytime that I want to go from grams to moles you guys have to remember that we use the molar mass, and that's going to come from the periodic table. Excuse me. So I'm going to do times fraction bar, because that's what we always do in conversion problems. And I can put this over 1 just to remind myself that it's a fraction. So grams is at the top. I need to put grams at the bottom in order for it to cancel. And the unit that I want is moles. And I said that I was going to need a periodic table, so I'm going to get out a periodic table, and I'm going to look for magnesium. There is magnesium. The molar mass is the number at the bottom. So I have 24.305 grams of magnesium. Remember, that number, whatever number is at the bottom, in our case 24.305, that's always grams, never moles. You always put that number with the grams. So grams of magnesium is down here, so I put it here. 25.305 grams of magnesium. And whenever I get this number, it always goes with 1 mole. All right, well, grams magnesium cancels, and I'm left with moles of magnesium, and that's what I want. That's good. So I'm going to go ahead and do the math there. So if I get a calculator, okay, so I'm going to take 0.07 divided by 25.305, and that gives me 0.0027. But before I do anything, I need to check for sig figs. In this number, I only have 1 significant figure. Remember, if there is no number in front of the 0, that 0 does not count. So this is just 0, not significant. 0, not significant. But as soon as I see that counting number, it is significant. So now I have 1 sig fig. This doesn't count, that doesn't count. Here I have 5 sig figs. So my answer, when I'm multiplying and dividing, must have the smallest number of sig figs. In between 1 and 5, I need to have 1 sig fig in my answer. So this 0 doesn't have anything in front of it, so it doesn't count. So not significant, not significant, not significant, significant. 2 is significant. Well, if I look behind it, there's a 7. As long as that number is greater than 5, I can round up. 7 is greater than 5, so my answer is 0.003. So I'm going to write that there. 0.003, and my unit again, moles of magnesium. All right, number 1. Now we're going to do the same process, but for oxygen. I'm not going to do it because if you weren't here, I want you to do it. So I'm just going to go ahead and skip that. Down here, to find your molar ratio. All right, well, I'm not going to be able to find the ratio without you having found the moles of oxygen. So I'm going to have to pause there and I'll skip it. If you have questions, you can come find me during class. Okay, this part you're also going to have to figure out on your own. If you have questions, you can find me after class. Number 5, here it says verify and compare the true value. So we want to look at magnesium. In reality, what we did was experimental, but if we were to theoretically think about it, magnesium is in group 2, which means that magnesium has 2 valence electrons. But magnesium, just like every other atom, wants 8. Well, it's easier for magnesium to lose 2 than to gain 6. So magnesium will lose 2 valence electrons. So loses 2 electrons. And if I lose an electron, then my formula, my magnesium, is going to become positive. And he lost 2, so he is positive 2. Each electron is negative. So if I lose 1 negative electron, I become positive. If I lose 2, I become positive 2. I'll let you guys try and work out number 6 for oxygen. All right. The rest of these questions, you're going to have to come and find me or ask some friends because I want you guys to think about it without me just giving you the answer straight away. Down here, we have this chart. On this chart, you're going to have to put cations at the top, and I want you to write anions down here. Okay. So what kind of elements form cations? Metals or nonmetals? I hope you said metals. And I hope for anions, you would say nonmetals. The reason is metals like to lose electrons and thus become positive, whereas nonmetals gain electrons and thus become negative. So on this chart, what you need to do is pick 3 metals and 3 nonmetals. I'm going to do one for you. So I do not want you to choose transition metals. Please do not choose a transition metal. Just choose metals from either group 1 or group 2. I like lithium, so I'm going to go ahead and pick, actually I like magnesium. Let's go ahead and pick magnesium. So Mg. And we already said magnesium is in group 2. Therefore, magnesium has a charge of 2 positive because it will lose his 2 valence electrons, so 2 positive. Now I'm going to pick a nonmetal. Well, coming back to the periodic table, my nonmetals are on this side. I do not want you to pick a noble gas because noble gases do not form ions. Noble gases are perfect. They already have 8 electrons. They don't want any more, so we're not going to pick that. I'm going to pick nitrogen. I like nitrogen. He's in group 5, and I know I find the group number by saying I find the charge by saying the group number minus 8. So nitrogen has a charge of 5 minus 8, negative 3 for group 5. All right, so nitrogen, which is just N, is going to have a charge of negative 3 because he's in group 5. You're going to pick 2 more nonmetals and put their charges here. Please do not pick anything in group 4. Group 4 is weird. Just ignore it. Do not pick anything from group 4. All right, at this point, I want you to combine these 2. Well, if I take magnesium and nitrogen and I combine them, well, magnesium is positive 2. Nitrogen is negative 3. Right now, positive 2 and negative 3 do not add up to 0. Therefore, I need to find the least common multiple. My least common multiple in between 2 and 3 is 6, right? Because if I did multiples of 2, let's see, 2 and 3, multiples of 2, 2, 4, 6, multiples of 3, 3, 6, 9, etc. The smallest multiple they have in common is 6. So I need to multiply this by a number to give me 6. 2 times 3 is 6. 3 times 2 is 6. Whatever I multiplied it by, these numbers tell me how many of each of these atoms I need in order to make a neutral compound. So my final answer would have been Mg, and I have 3 of them, so I'm going to put a 3, and N, and how many nitrogens? Should have been 2. That was my final answer when I combine magnesium and nitrogen to form magnesium nitride. Now you're going to do the same thing. I'm just pretending, let's say I picked lithium with a positive 1, and maybe, I don't know, strontium with a positive 2. And maybe down here I pick something like fluoride, and maybe something like, I don't know, I don't like oxygen. We've done oxygen too much. Let's do sulfur. So you would then take magnesium, combine it with this guy, and put his compound. Magnesium, combine it with this guy, and put his. Him with him, here, him with him, etc. Okay, so you should have all of this filled out with 9 different compounds based off of these combinations. All right, coming down here, we have the mass percent. This is for my honor students, the mass percent. Down here, this is for all my students, but up here, mass percent just for honors. If you guys recall, the mass percent is equal to the mass of the part divided by the mass of the whole times 100%. Okay, so let's look over here and find the mass percent of magnesium. Well, it gave you a nice little formula. You can do that, that's fine, but I'm just going to do it without looking at the formula. So I know that the mass of magnesium, this is the part that I'm interested in, is magnesium, is going to be, back from my data, 0.07 grams. So I'm going to put that at the top because that's the part I'm interested in. 0.07 grams of magnesium. And I'm going to divide that by my whole. Well, my whole compound was magnesium and oxygen. See, magnesium and oxygen. So I need to add 0.07 grams, that's of magnesium, plus the mass of oxygen, which I found was 0.04. So 0.04 grams of oxygen. All right. And then lastly, I need to multiply that by 100. So times 100%. going to do that on the calculator. So 0.07 divide by parentheses 0.07 plus 0.04 end parentheses equals times 100. And my answer was 63.6. So that equals 63.6. After the 6 was a 3, so I don't have to round up. All right, any calculation requires sig figs. So let's check out sig figs. How many sig fig in this number? 1. And here, these two both have 1. So my answer should only have 1 significant figure. Well, this number has 1, 2, 3 significant figures. That's not correct. So my first significant figure is this one. I look here. Is 3 greater than 5 or less than 5? It's less than 5. So I need to make it just go away. However, 6 is not the same thing as 63. If you're supposed to get a paycheck of $63 and I give you 6, you're going to be mad at me. So I need to put something here to hold the value. Well, if I put a 0, well, $60 is way closer to 63. So 60, putting that 0 holds the value. But now I just have 1 sig fig. Please be sure you do not put a decimal. As soon as you put that decimal, this 0 becomes significant and I now have 2 sig figs. But as long as I don't put a decimal, the 0 is not significant and I only count the 6. So this is 1 sig fig. So this should be 60% magnesium. Okay? I'm going to let you work out the mass percent of oxygen. All right, down here, the very last part of the lab. So this is basically giving you the same exact thing that we did in the beginning of lab, except for now I'm giving you new numbers. So here we can see 20.30 grams of a sample. And this is a sample containing not magnesium, but phosphorus and oxygen. All right, well, in this case, it's telling me that this entire sample, all of the phosphorus and all of the oxygen, weighs 20.30 grams. And it's also telling me that 8.87 of that is just the phosphorus. So I have mass of the sample, so this is the phosphorus and the oxygen, and then I have the mass of just the phosphorus. So mass of the phosphorus and the oxygen, it was given to me, see? This is the mass of the sample containing phosphorus and oxygen. And then I have the mass of just the phosphorus. How can I find, for number 1, the mass of the oxygen? Well, if I subtract, the phosphorus goes away and I'm left with mass of oxygen. So this number will give me the mass of the oxygen. All right. I want you guys to try and work this out just like the way we worked out all of the information here. Okay, very good. If you have any questions, please come and see me Monday. But if you were absent either on Thursday or Friday, I do expect for you guys to watch this video so that you can have some understanding of the lab.